Okay, now let's convert a sawhorse representation for what we'll find to be an eclipsed conformation into a Newman projection and vice versa. So I'm going to do that with this model, and I'm going to draw my bold dashed eclipsed conformation and then convert that to a Newman projection. So here's my molecule, and my key for looking at whether something's staggered and eclipsed is I always look at the bonds that are in the plane of the screen. So if I kind of rotate this molecule, what you can see is that the bonds here, when I orient it like this in this sawhorse, the bonds that are between the light green to carbon, carbon to carbon, and carbon to red group, those are in the plane of the screen. And just as kind of a mnemonic here, if I kind of tip that on its side, that's going to give me an E for eclipsed without the center. So again, this is a sawhorse representation, and this is going to eventually, as we're going to find, this is going to be an eclipsed sawhorse. But when you see the bonds that are in the plane, and they make this U shape, which if you turn on its side is almost an E, then that will tell you that we indeed have an eclipsed sawhorse. Now I'm going to rewrite that structure up here, and we're going to go ahead and we're going to add our bold and dashed wedges. So here is the light green group, and here is the red group. Okay. Now this white group down here and the purple group are both in front of, they're pointing towards you, and they're in front of that plane. And again, if I just kind of rotate my molecule a little bit here, you can see that the white and the purple are indeed pointing towards you. So what we would have is we would have then our white group on a bold wedge pointing down and to the left, the purple group pointing down and to the right. So here's my purple group, and here's my white group. Now the green group and the gray group are both pointing back away from behind the plane, as you can kind of see here. They are pointing away from you, and so they should go on dashed wedges. So my dashed green group down and to the left, and my dashed wedge gray group down and to the right. Okay. So this is then a bold dashed representation of the eclipsed sawhorse, using this model as my guide. Okay. And if you have a model set, you could go ahead and set it up and look at it and do this exact same thing. Now, I want to turn this into a Newman projection. You may say, I don't know necessarily, yeah, you told me if you tip it on its side, it's eclipsed because it's missing the E. That's the mnemonic you're telling me to use. But I can't really see that this is eclipsed. And that's exactly what Newman helped us figure out by coming up with Newman projections. So in this case, what I'm going to do is I'm going to view myself over here looking down the carbon-carbon bond, looking down the bold dashed wedge bond. So if I do that, what am I going to see? Well, let's do it. Now, if we had virtual reality, we could actually sort of walk in this world, and we do have virtual reality that computer science students built for us, which I'll show you later on, maybe. Best thing I can do in this case is, okay, let's look down the carbon-carbon bond. Let me just go ahead and rotate this molecule so we look down the carbon-carbon bond, and let me move it over here. So now I'm looking down the carbon-carbon bond. Okay, so there I am. That's what I'm seeing. Now, in this case, the front carbon is the one with the light green and the white group on it, which, if I just kind of rotate this a little bit, you can see that was indeed the front carbon. So this is my front carbon. And then this is the back carbon, the one with the red, purple, and gray. You can't see the back carbon because it's obscured by the front carbon. And that's what Newman did, was he came up with a way that we could represent this viewpoint by saying, okay, this intersection point is my front carbon and the big circle is my back carbon. And in this case, what happens is these groups are right on top of each other. They're not right on top of each other. They're just parallel to each other, right? So in the Newman projection, at least the way I draw it, and some textbooks might be a little bit different, what I like to do is I like to then draw my bonds parallel coming off the circle, which means that those are attached to the back carbon. Okay, so attached to the front carbon, what did I had? I had the light green group. I had my green group, which now is to the left, and my white group is to the right. Okay. So if you're up here kind of looking at that, you can see, okay, you can imagine yourself. I'm looking down here. My white group is to my right, and my green group is to my left, which is exactly what you're seeing here. On the back carbon, what's going on? Well, the purple group is to your right. The gray group is now to my left. Okay. And then what's the red group? The red group is straight up with the light green group. So what we have is we have the light green and the red group are basically eclipsing each other, right? They're down here. They're in the eclipsing interactions. And all of these groups are eclipsing each other, right? The two bold wedge groups are eclipsing each other. So these were the bold wedge, and the gray and the green, they are the dashed wedges. So the perspective of getting from a Newman projection back to a Sawhorse representation is to say, well, I'm over here looking at the carbon-carbon bond, and that's how I can go from the Newman back to the staggered. So what I'm doing is I'm over here, right? So as I look at that, I go back to my original viewpoint, right? I'm over here looking at that original viewpoint. So that's how we can interconvert between the Newman and the eclipse conformation. So the groups that were on the right are bold. The groups that are on the left from this side are dashed. And again, my telltale sign in this, what I use to tip me off that this is indeed an eclipsed Sawhorse, is I look at the groups that are in the plane. So there are my groups that are in the plane. Now, what does that represent in the Newman? It represents these groups right here. Because if I'm over here looking at that, at the molecule, that's what I'm seeing, right? I'm seeing those in the plane. So hopefully that makes sense in terms of trying to convert a Sawhorse into a Newman and vice versa. So with this model. So again, if you're starting out with the Sawhorse, the molecule would look like this. And then if you're over here looking at it, it would look like this. Okay. So that's how we can interconvert between these two, the Sawhorse and the Newman. Okay, so hopefully that makes sense.